If the graph is connected means there is a path between every pair of vertex A to B, then B to E. This is called as connectivity between two vertex. There is no path from traversing from A to F, so it is a disconnected graph. We are choosing the shortest route from source to destination. Hello everyone, welcome back to my new session. I am Shweta, Computer Science faculty, Vidhyaashram First Grade College, Mysuru. In my previous session, I have discussed about Hamilton graph and Hamilton circuit and example problems. So today I am explaining the very important new concept called shortest path problems. So what is this shortest path problems in graph theory? If students wants to reach from home to school or college to school, they will choose the shortest path, right? In shortest path method, we are choosing the shortest route from source to destination. So before that, I would like to explain about connectivity. So what is this connectivity? A graph is said to be connected. I hope you know about connected and disconnected graph, right? A graph is said to be connected if there is a path between every pair of vertex. If the graph is connected means there is a path between every pair of vertex. From every vertex to any other vertex, right? There is some path between every pair of vertex from one vertex to another vertex. There should be some path to traverse from one place to another place, from one vertex to another vertex. There should be some path between every pair of vertex. So this is one connected graph, right? And that is called the connectivity of a graph. There should be a path between every pair of vertex. Clear? This is called as connectivity. And a graph with multiple disconnected vertices and edges is said to be disconnected. So what is connected and disconnected? There should be multiple disconnected vertices and edges is known as disconnected graph. In connected graph, there should be a path between every pair of vertex. That is called as connectivity of a graph. 2 marks question. So just write the definition and example. And example for connectivity. Here I have one graph. Here it is possible to travel from one vertex to another vertex. Is there any path? Yes, we have one path from every pair of vertex. Example, one can traverse from vertex A to vertex E. So here I have vertex A, vertex B. So this is connected graph. There is a path between every pair of vertex. So A, B, E, D and C. So here I have 5 vertex A, B, C, D, E. So now I have to find the connectivity. So here there is a path between every pair of vertex. Vertex A to vertex E. So just observe this. Vertex A to vertex E. To travel from vertex A to vertex E, there should be one path, right? So there should be a path between every pair of vertex. For traveling from vertex A to vertex E, we have one path, that is A to B, then B to E. Clear? So traveling from A to E is A to E. We have one path, that is A to B, then B to E. This is called as connectivity between two vertex. There should be a path between every pair of vertex. And now, so traveling from B to D. So B to D is, this is a path traveling from B to D, and traverse from A to D is, there should be a path from A to C, then C to D. This is called as connectivity. This is an example for connectivity. You can give any other examples. And now, second example. In the following example, traversing from vertex A. So, in this example, I have vertex A, B, C, and DEF. So traversing from vertex A to vertex F. Traversing from vertex A to vertex F is not possible. So how would you travel from vertex A to vertex F? It is not possible because this is different and this is different graph. So it is not possible to travel from vertex A to vertex F because there is no path between them directly or indirectly. Hence it is a disconnected graph. Clear? It is a disconnected graph. There is no path from traversing from A to F. So it is a disconnected graph. Clear? There is no connectivity between two vertices because these are the disconnected graph. Clear? So this is about your connectivity. It is 2 marks question. And the next concept is shortest path problem. So what is this shortest path problem? The name itself indicates we are finding the shortest path. Clear? So in graph theory, the shortest path problem is the problem of finding a path between two vertices. We are finding a path between two vertices. Clear? So now V1, V2, V3, V4. We are finding the path between two vertices or nodes in a graph such that the sum of the weights of its constituent edge is minimized. So here in shortest path problem, we are choosing the shortest route from source to destination. Example, V1 is a source and V3 is my destination. So from traveling from V1 to V3, we are finding a shortest route. Clear? This is called as shortest path problem. And types of shortest path problem. We have 4 types in shortest path problems. That is single pair shortest path problem, single source shortest path problem, single destination shortest path problem, and all pairs shortest path problems. I'll repeat. Types of shortest path problem: single pair, single source, single destination, all pairs shortest path problems. Here we are using this single source shortest path problem. Clear? So we are using this concept of single source shortest path problems. So which are the single source shortest problem we are studying? So that is Ditsch's algorithm. Ditsch algorithm is the shortest path algorithm. So Ditsch algorithm is a very famous algorithm. So how to pronounce this? Ditsch's algorithm. So it's a famous algorithm. It is used for solving the single source shortest path problem. So this Ditsch algorithm we are using for solving the single source shortest path problem. It computes the shortest path from one particular source node to all other remaining nodes of the graph. Listen carefully. This Ditsch algorithm we are using for finding shortest path from one particular source node to all other remaining nodes of the graph. Example, if you have this graph V1, V2, V3 and V4. So in this graph we are applying Ditsch's algorithm. So here we are finding the shortest path from one particular source. Example, V1 is my source node to all other remaining nodes of the graph. So V1 is my source node. To traveling from V1 to V3, V4, V2, we are finding the shortest route. And this algorithm aims to find the shortest path in a directed or indirected graph with non-negative edge weights. All the edge weights should be a positive. Clear? So all the edge weights should be a positive in Ditsch's algorithm, and it can apply only for directed and indirected graphs. So this Ditsch's algorithm used only for directed and undirected graph. Clear? So we are applying this Ditsch's algorithm concept only for directed and undirected graph with positive edge weights. We can apply only this for positive edge weights and for direct graph and for undirected graph only. And the conditions in Ditsch algorithm. So which are the conditions we can apply in Ditsch algorithm? Ditsch algorithm works only for connected graphs. Clear? We can apply this only for connected graphs, and the actual Ditsch algorithm does not output the shortest paths. It only provides the value or cost of the shortest path. So by using the direct graph and indirect graph, we can find the shortest path in Ditsch algorithm. And the graph should not contain negative edge weight, and graph should be works for directed as well as undirected graphs. Clear? We are applying this Ditsch algorithm for finding shortest path. Clear? So let's understand this Ditsch algorithm step by step. So how to implement this Ditsch algorithm? So step 1, in the first step, two sets are defined. So this Ditsch algorithm can apply only for directed and indirected graph. Example, here V1, V2, V3, V4, V5 and so this is one directed graph. So here we can apply this condition for positive edge weight. Example, 5, 2, 3, 4, 6, 7, 8. We can apply this only for positive edge and directed as well as indirected graph. So first step is initialize distance according to the algorithm. Example, you can choose any source node. So first I will take, yes, source node is my V1 vertex. So pick first node and calculate distances to adjacent nodes. So first I have picked this V1. V1 is my source node and I can travel from V1 to V2, V1 to V3, V1 to V5, etc. So here after finding the source node and destination, we can pick next node with minimal distance, repeat adjacent node distance calculations and final result of shortest path tree. So now I'll explain with an example so easily you can understand about Ditsch algorithm. So first example problem in Ditsch algorithm. So here I have one undirected graph. I will apply Ditsch algorithm. So first you have to check the vertices. We have 5 vertices, 1, 2, 3, 4, 5 and we have positive edge weight. So it should be a positive edge weight and directed as well as undirected graph. So then only we can easily apply the Ditsch algorithm. So we have 5 vertices and 5 edges, right? So what is the first step in Ditsch algorithm? So first you have to choose the source node. So now I will select the first node as my source node. By using the source node, I can traverse from each and every node and I can find the shortest path. I can find the shortest route in Ditsch algorithm. So now I have to find the optimum solution. So by using this Ditsch algorithm, if you are applying the Ditsch algorithm, so easily you can get the optimum solution. Clear? So first step is source node is 1. And first list all the vertices 1, 2, 3, 4, 5. So starting node will start from initial value that is 0. Clear? Starts from 0 initial value and remaining values are starts from infinity. Keep in mind value starts from source node value starts from 0 initial value and the remaining values are infinity. So now from vertex 1 is connected to vertex 2 and vertex 4. I'll repeat. Vertex 1 is connected to vertex 2 and vertex 4, right? So I can check the edge values. So it is 4 and 8. So initial value starts from 0. So 1, vertex 1 starts from 0 and this vertex 1 can travel to vertex 2 and vertex 4. It's connected to vertex 2 and vertex 4 and not to vertex 3 and not to vertex 5. So now I have to find the shortest path among this. So 1 is connected to 2. So 1 is connected to 2. The edge weight is 4. So now 0 plus 4. Why it is 4? Travel from 1 to 2. Edge weight is 4. So now I am traveling from 1 to 2. So 0 plus 4 is 4. And again I will repeat. So vertex 1 value starts from, weight starts from 0 and it can travel to 2 and it can travel to 4. So here vertex 1 and vertex 2 edge value is 4. So 0 plus 4 is below in vertex 2 you can write it is 4. Clear? And from travel from 1 to 4 vertex edge value is 8. So 0 plus 8 is, it is 8. So 1 is connected to 2 and 1 is connected to 4. So below in 2 and 4 have written the edge weight. So the remaining edges are same. Clear? And now among these values, which is a minimum value? Minimum value is 4. Clear? The minimum value is 4. So before that you have to scratch this vertex 1 because already we have visited this vertex 1. So again you can't repeat this back. Clear? So I have strike out this 1. So now I can't visit it again. So this is 1 and vertex value, least vertex value is 4. Then I'll write this 2. And now 4 is a minimum value. It comes under vertex 2. Clear? 4 is the minimum value. It comes under 2. So 2 is connected to 3 and 2 is connected to 1. So you can't go back to the 1 because already it visited to 1 vertex 1. So you can't go back to the first position again. So 2 is connected to only 3. So 4 plus 3 is equal to 7. And the remaining edge values are same. So it is same. So now again I'll scratch this because I have visited the vertex 2. So no need to use this again. And here among these three values, which is the least value is 7. So 7 comes under vertex 3. I'll write vertex 3. So vertex 3 connected to vertex 4 only and vertex 2. So vertex 2 already I have visited. So no need to go back to the vertex 2. So now vertex 3 is connected to 4. What is the edge value? Edge value is 4. So here among these values, edge value, minimum edge value is 7 and 7 plus 4 is what? 7 plus 4 is equal to 11. So 7 plus 4 is equal to 11. But here you can't write 11 because 8 is lesser than 11. So you have to choose the least value. Clear? So 8 is lesser than 11. So again you can repeat the same value because 8 is lesser than 11. You can pick only the least value. Clear? So 8 is less than 11. So I have written only 8. So again you just scratch this vertex 3 also. So now you have only two vertex 4 and vertex 5. Among these two vertex value 8 is a minimum value. So I will take this as a consideration. So 8 comes under vertex 4. So now 8 means vertex 4. So this vertex 4 is connected to vertex 5 and vertex 1. So vertex 1 already we have visited. So no need to go back to the first vertex. And vertex 4 is connected to vertex 5 only. So here the least value is 8. 8 plus 7 is 15. So to travel from vertex 4 to vertex 5 is 15. So 15 is lesser than infinity. I'll write it is 15. So here I have cancelled this 4 also, vertex 4. And this is the last consideration is vertex 5. Clear? So this is your, again I'll repeat. So here we have one connected graph and it is undirected graph. So how many vertices are there? 1, 2, 3, 4, 5. We should have only the positive edges. Clear? So here first you have to choose the source. So source is 1. So vertex 1 is my source. So if you want to travel from source to destination, we have to choose a shortest path among this vertex. So first I will choose source node is 1. So vertex 1 is my source node. To travel from vertex 1 to vertex 1, vertex 1 to vertex 1, the edge weight is 0. It should start from initial value. So 1 to 1 is 0. It is always 1 to 1 is 0. And the remaining values are, edge weights are infinity, 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 etc. So all the first values are common in every problem. And in second step, so 1 is connected to 2 and 1 is connected to 4. 1 is connected to 2 and 4. So now what is the edge value of 1 to 2? 4. So 0 plus 4 is 4. And 1 to 4 is 8. So 0 plus 8 is 8. So 1 to 2 is 4. 1 to 4 is 8. So among these value, infinity is higher than 4, right? So I have written the least value. So infinity is higher than the value 8. So I have written the least value. So among these value, least value is 4. So I have selected this least value. So first I will scratch this vertex 1 because already I have visited vertex 1. So now in the second step the least value is 4. So 4 comes under vertex 2. So 4 is my least value and 2 is connected to 1, 2 is connected to 3. So 1 we can't visit because already I visited and 2 is connected to 3. So 4 plus 3 is equal to 7. In the next step 4 plus 3 is equal to 7 and 2 is not visited to 4, 2 is not visited to 5. So as it is, I have written the same value. So now in the next step, among these three value, least value is 7. You just strike out this because 2 already we have visited. And among this value, least value is 7. I have selected this least value as a 7. It comes under vertex 3. So vertex 3, you just strike out this. Vertex 3 connected to vertex 2 and vertex 4. So you can't choose this again. And vertex 3 is connected to 4. So 7 plus 4 is equal to 11. So 11 is higher than 8. So I have written the least value again 8. 11 is highest value than 8. So I have written 8 only. And 8 comes under vertex 4. You just strike out this and choose this vertex 4. So vertex 4 is connected to vertex 1 and vertex 5. And the edge value is 7. So 8 plus 7 is equal to 15. So in the next step for vertex 5 I have written 15. So infinity is higher than 15. So I have written the least value as 15. So now the consideration has finished. So traveling from 1 to 1 it is 0. Travels from 1 to 2 it is 4. From 1 to 3 it is 7. 1 to 4 it is 8. 1 to 5 it is 15. I'll write source is equal to, so how many vertex are there? 1, 2, 3, 4 and 5. Travels from 1 to 1 it is 0. 1 to 2 is 4. 1 to 3, 7. 1 to 4, 8. 1 to 5 it is 15. Clear? So now I will find out shortest path and shortest distance. So shortest distance, to traverse from 1 to 3, traverse from 1 to 3, it is 7, right? Shortest path is 7. To traverse from 1 to 3, shortest path is 7. Clear? So 1 to 3, shortest path is 7. So 7 comes under vertex 3, right? 7 comes under vertex 3 and now I will take this as a consideration and I will travel from the next position. So if the value is changing from this value to this value, so value is changing, here it is 7 and here it is infinity. So I can jump to 4 because 4 is the least value than 7, right? So now 7 is the least value. So 7 is changes to 4 because 4 is the least value. So this 4 comes under path 2. And now again I'll jump to the next position. So previous position, the least value is 0. Clear? Now I am finding the shortest path. Shortest distance is 1 to 3. If you want to travel from 1 to 3, shortest distance is 7. Now I have to find the shortest path. So traveling from 1 to 3, shortest distance is 7. And now I will take this as a consideration. 7 is a consideration. So now 7 comes under path 3. 7 comes under vertex 3. And next I have to travel from 3 to 2. For traveling from 3 to 2, I can choose the least value. So in vertex 2, the least value is 4. So 7 is higher than 4. So I will choose 4 is my least value. So 4 comes under path 2. And again, from traveling from 2 to 1, we have one least value, that is 0. So 2 to 1, least value is 0. So 0 is least than 4. So 1 is my least path. So the path from 1 to 3 is 3 to 1 or 1 to 3. So 1 path value is 0 plus 2 path value is 4 and 3 path value is 7. It is 11. Clear? The shortest distance from 1 to 3 is 7 and the shortest path is 3 to 1. So you can also write 1 to 3. So travel from 1 to 3. 1 to 2. 1 to 2, the shortest path distance is 4 and 2 to 3, shortest path distance is 3. So 4 plus 3 is equal to 7. So 7 is my least shortest distance. Clear? This is about your Ditsch algorithm. Don't get confused. Please understand the logic. So first you have to use directed as well as undirected graph and consider each and every vertex. So you have to visit each and every vertex exactly once. You should not repeat the path again and again and use the positive edge weights. And write this table and easily you can find the shortest distance and shortest path. Clear? So this is about your Ditsch algorithm. It is very simple concept. Definitely there will be a problem on this concept. So you can expect for 7 marks or 8 marks in Ditsch algorithm. So today you learned the concept of connectivity and Ditsch algorithm. So in my next session, I will come with a new problems in Ditsch algorithm. Thank you.